Okay, folks, here we are, 3.32, talking about the predictive distribution. So it's going to be a pretty quick section. So let's get into it. Okay, so what he's saying is we're not usually interested in the value of W itself. So remember, in this setting, we have in this case, we'll have a scalar output, so one-dimensional output that we're going to try to predict as being a linear combination, according to these weights, of some features. So remember that we had our y given x and all the other parameters was going to equal to these weights projected onto our features computed for a given input. So again, supervised learning, we're given x, we want to predict y, and we're going to say it's this kind of weighted combination. I'll write this out again. It's wi of phi I x. So we compute a series of features on a given input, and we weight them according to W. Now, what he's trying to say here is that in many settings, we don't actually care that much about what these weights are. What we want to do is use those weights and our uncertainty in those weights to predict new values. So we have a data set of x's mapping to y's, and now we're going to think of it as in some way kind of compressing the information in that data set into this weight vector. And not just, in this Bayesian setting, it's not going to be just the value of the weight vector. It's going to be a whole distribution on what that weight vector could be. And now we want to use that knowledge to predict a new value. So how are we going to do that? Well, it requires that we evaluate the predictive distribution. So notice that what does this predictive distribution look like? Well, it's still a probability distribution over the new value t, given our target values and our hyperparameters. And how is it computed? Well, it's computed by integrating over our knowledge of W. So that's over here. That's kind of our uncertainty we built up from this data set. So which is conditioned on the data and the hyperparameters, and then our model of how you get the outputs given a set of those weights. So notice what we're doing here. So this thing is just the actual model saying, given some weights, how do I predict the output? And that's going to be this kind of linear thing. But because we're doing this whole, we're doing the Bayesian approach, we're not going to just take a single value of W. We're going to actually integrate the contributions from, over the entire distribution of weights based on, the uncertainty that's kind of captured in this probability distribution. So if this probability distribution is kind of very sharp around its peak, then that might be like the frequentist setting where we just report the value for a single setting of the weights. But often, and we saw in the previous example, let's say if you don't have that many data points or data is very noisy, you're going to have uncertainty over W. And what we do here is we actually integrate over that uncertainty. So we kind of add up the contributions of all the different values W could take, should be here, weighted by our uncertainty, or the probability that it could take that value. Okay, so in which t is the vector of target values in the training set, and we have omitted the corresponding input vector, so there's going to be an x as well that we're going to just leave out for now. And the conditional distribution, p of t given x w beta of the target variable is given by 3.8. So that was this thing basically, and with some additive noise. So we're going to say that if you give me the input and the weights, well, the output is just this weighting, but there's going to be some noise on top. And the posterior weight distribution is given by 3.49, and we're not too far. So let's just scroll up and see what that looks like. So it's this thing, right? So we figured out in the previous section that once we've incorporated all the information from our data set, then we're going to have some mean that's going to be a weighted combination of the prior and what our data gives us, and in this case, it's going to be precision, which is a sum of the precision from the prior and our data points. So once we've got this, we've got a kind of a Gaussian thing for encapsulating our uncertainty in the weights. And we've also got a Gaussian, this distribution will also be Gaussian. And so when it turns out, it's a very convenient property that if you're kind of integrating one Gaussian against another, the result will also be a Gaussian. And so all we need to know is what's the mean and the variance of that Gaussian. And it turns out we've actually kind of done some of this work, so you can go back to that important table of kind of how to work with Gaussians in 2.115, and the idea there was essentially, we had a setting there where we had, and I'm going to put it in the language that it shows up there, so the probability on some x, and then we had p of y given x, and we were interested in like the marginal probability of py. So how do you get that? And it was kind of a d of x. So the x's kind of corresponds to w's here, and the y's corresponds to t's, and that's what you're getting. And all of these conditioning terms are kind of they're being conditioned on the whole way through, so you can kind of just the results go through as long as you just put this bar with the conditioning everywhere. But basically, this is the setting that we're in. And so one way of looking at this is just go on recognizing that that's the situation you're in and just plugging in the values, and it tells you that the results. So this is the posterior distribution on the output is the projection of so you're given some new x, you project it onto the mean of the weights, and there you also have a variance. That variance is the variance coming from the noise plus some variance coming from your uncertainty in the weights. And so he says, the first term of 3.59, so this guy represents the noise in the data, so you're always going to have that, whereas the second term reflects the uncertainty associated with the parameters w. Because the noise process and the distribution of w are independent Gaussians, their variances are additive, right? So the noise doesn't really matter on what our uncertainty about the weights are. They're just going to be additive independent noise. As a consequence, it can be shown, this is a good exercise to do, 3.11, that our variance is always going to be either the same or decreasing, so less than or equal to. And as we get an infinite amount of data, well, then we're going to get extremely certain about where the weights are, but that doesn't mean that we will have no uncertainty in the outputs, because there's still always this additive noise. So this term will converge to 1 over beta, because we know what the weights are, but there's still this kind of unresolvable uncertainty coming from the noise. Yeah, solely from the additive noise governed by the parameter beta. Okay, so now we're going to try it out. So let's go have a look. As an illustration of the predictive distribution for Bayesian linear regression models, let's go to the synthetic sinusoidal data set. So here is our data set. So the green, I'll just do this one because I know you guys can see that. So the green here is the true mean. These are the points that we're contributing, that we're observing. This is the mean of the resulting distribution. And the way it's computed is he will essentially, for every single value of x, he will go back to this formula and just compute the projection of the features onto the mean of the weights that you've computed for that point. So basically, this is being computed. This is being kind of computed pointwise, and the variance are also being computed pointwise. So at every single point, you go and compute the projection of phi of x corresponding to that onto the covariance that you've computed after observing, for example, 2 data points. And as you can see that over time, so there's kind of a couple of things to notice here. As we observe more and more points, well, the uncertainty is always lowest around those points, because having observed those points, we're pretty sure, we're more certain about what the value of the function is going to be at those points. And as we collect more data points, well, the overall kind of variance is coming down. So you can essentially, it's just because the points are essentially constraining the form of the function. So once you've got I don't know, 20, 30 points here, you're fairly sure what the shape of the function is. But notice that you still have this band, right? And that's just coming from the variance, that the noise variance, basically. Right. So data sets are shown. The red curve shows the mean of the corresponding Gaussian predictive distribution, and the red shaded region spans 1 standard deviation on either side. So what we just discussed, note that the predictive uncertainty depends on x and is smallest in the neighborhoods of the data points, and the level of uncertainty decreases as more data points are observed. Okay, now he says, as he says, so the plots only show the pointwise predictive variance as a function of x, right? So again, as I said, the way we compute this is we just go for every single point, along x. We'll discretize it to very tiny steps, and we'll just compute the variance around each point and the mean. But you want to see, well, that's just kind of telling you at a single point. But how does what about the shape of the function as a whole? So in order to gain insight into covariance between the predictions at different points of x, we can draw samples from the posterior distribution over W, and then plot the corresponding functions as shown in 3.9. So this is kind of saying, so if you want to see kind of what functions are coming from, what functions your uncertainty over W implies, well, the way to do it is just to you can take your distribution of P of W given your data, sample W from it, sample weights from it, and then just plot the function, these functions for those values W. And to do that a bunch of times, you'll kind of get a sense of how your weights constrain the functions that can fit your data. So let me see if I can, so here is kind of what that looks like when you've observed a single data point, and you can see that for a single data point, obviously there isn't, it's kind of like that linear regression setting, right? Like you're basically unconstrained, but you do know that these functions will tend to go through this point, right? So that's kind of what you see here. Like with one data point, the functions go through there, so you can see all of them. They're all squiggly in different ways, but they are going close to that point, that's as much as 1 point tells you. Once you've got 2 points, well, the functions have to go through 2 of those points, more or less, and so it constrains you a bit further. As you gather more and more points, eventually, your shape becomes quite constrained. There's still variability, but you're now kind of living in a kind of very small band. So that's what that's about. The final point, which is actually really quite interesting and good to know, is if we use localized basis functions such as Gaussians, so if our feature vectors were those Gaussians, then in regions away from the basis function centers, the contribution from the second term in the predictive variance will go to 0, leaving only the noise contribution. Thus, the model becomes very confident in its predictions when extrapolating outside the region occupied by the base function, which is exactly what you don't want, right? Extrapolating outside of the region that its basis functions can actually change, can affect the prediction, but somehow it's getting very confident. Why is that? Well, if we go back to this expression, you'll notice that we've got 5x projecting, we're computing the projection of the variance onto the direction 5x. Now, if 5x is 0, well, then this whole thing is going to be 0. So 5x, remember, for our basis functions, we had forms like this. Now, suppose that the x that we had sampled was kind of somewhere out here, out of the range of all of the basis functions. Well, now this 5x, our feature vector for that input is going to be 0, and so we're going to be like, oh, well, our variance is just the noise variance, but actually it's just reflecting, it's kind of a degeneracy. It's reflecting the fact that our variance, actually, our features don't actually say anything about that part of the space. And so that's actually a problem, and he says that later on we'll see, he said this problem can be avoided by adopting an alternative Bayesian approach to regression known as the Gaussian process. So we'll see that in section 6.4. And then finally, he says, look, so we were assuming that just the weights were unknown, but if the beta, the noise variance is also unknown, then you can use a different conjugate prior, and we've already kind of talked about this. Given by Gaussian gamma distribution, and in this case, the predictive distribution is a student's t. Okay, and I guess there are a couple of exercises to work that out. One thing I just wanted to point out, just going back. So I think it's a very useful exercise to go and kind of try to derive this kind of from the first principles, then go and look at our table, see how you can how you will get the same result. One other way, it's actually, and I think we talked about it when we were actually in this section, that you can arrive at this result in kind of an intuitive way. So let me just erase some of this stuff. Look, you care about. You can just think about it this way, right? Let's get some space. Okay. Yeah, you guys can see. Very cool. Okay, so the idea is like, look, we know that our weights are going to be, are normally distributed with some mean. I'm just going to call it mu, and some covariance. And now our output, I'm going to drop the dependence on W, is going to equal to phi of x transpose times W plus some noise. I'm going to call that just noise with some, actually, noise and 1 over beta, right? And so you can just, the way you can reason about this is, well, as far as, for given x, is 5x is just a constant. Whatever it is, it's just a constant, those feature values, it's a constant. W is a Gaussian. And so you just have kind of a linear combination of Gaussians. So this whole thing is, and you're adding to it an independent Gaussian. So this whole thing is going to be Gaussian, which is great. And now you just want to know what it, so all you need to know is its mean and its covariance, right? So you can just say, well, the mean of this variable is going to be, well, 5x is just a constant, times, so it's going to be the mean of W. And this thing is going to be 0 because it's, noise with mean 0. And so, well, what is this? Well, this is just 5x transpose times, mu, or in our case, it's called m of n. And what's the variance? Well, the variance of y is going to be this 5x times the covariance of w times 5x. Plus, because these are independent noise, you just add the variance coming from the noise. So this is just going to be 5x transpose times, whatever it's called, s of n or sigma for us, whatever it is, right? So that's it. So you can just think of it that way, right? And you'll see that this is exactly the same formulas that we get. So here is, m of n is just the same as our mu, and you've got s of n showing up. So it's just, you can just look at, what is this variable, this output that you're interested in? Well, it's just a linear combination of a Gaussian random variable plus an independent Gaussian. Well, the result's going to be Gaussian, and you can just use basic results about how to compute means and variances to get the mean and variance. And that's all you need. So that's not kind of a third, maybe shortcut way of computing what you need. Okay, so I think that's all I wanted to say about this section. A pretty short one, but again, a useful one. And so I think the important things to remember is that we don't necessarily care about W itself. We care about making predictions, and this is the kind of the Bayesian way of kind of how to do this. And then finally, this final point he made is that just because that covariance distribution, that covariance has become small, it could actually be because you're venturing into a region that your feature vectors don't say anything about. So just to be kind of careful about that, and later on we'll see how to deal with that using Gaussian processes. Okay, so hopefully the video was useful. Please let me know, as usual, whether you liked it or you learned something, you didn't learn something. If there's a mistake, as always, please let me know. And I will see you next time when we have another short section talking about equivalent kernels. So hope to see you then.